All right, how's it going? Welcome back to another video here in the series on group theory. In the last video, we introduced kind of the second half of this section title, right? Which was the notion of a homomorphism, or in other words, a function that maps from one group into another, that has the specific property that when mapping between two different groups, the overall group structure remains preserved. And just to quickly remind ourselves what that is, what a homomorphism is. If we have some function f, which has a domain group, g comma star, and maybe it maps to a codomain group, h comma dot, then a homomorphism is going to have the property such that for all elements x and y in this domain group right here, this equation is going to be satisfied. So we must have that f of x star y equals f of x dot f of y, like this. Right? And in the beginning too, we're really trying to be thorough with our notation here to describe that on the left-hand side, because x and y are elements of G, they get acted on by the binary operation from G, the star or the asterisk. Whereas on the right-hand side, f of x and f of y are elements of H. So these elements interact through the binary operation dot defined on H. Okay. So this is the definition again of a homomorphism, but a lot of times we're gonna, as you're gonna see, we're gonna get rather lazy with our notation. And maybe it's bad too, but sometimes if there are several different products going on or several different times operations are being applied, it can get tedious to write out an asterisk or a dot over and over and over. So sometimes we'll see this more compactly written as f of xy equals f of x, f of y, like that. Okay, so hopefully this sounds familiar, right? Going over these things called homomorphisms. Just while we're at it too, then we went over a specific subclass of homomorphisms, which were the specific homomorphisms which were also bijective, right? And we called those isomorphisms. And isomorphisms, these are tongue twisters trying to say these words, right? But isomorphisms are useful for telling us if two groups are isomorphic to another, which conceptually essentially tells us that regardless of what group we are looking at, if they are isomorphic, then we can think of them as having the overall same algebraic properties. And we kind of came up with the analogy of having two different chessboards. No matter what the chessboards look like, you can still play the same game of chess on those two potentially very different looking boards. Right? So hopefully all that sounds familiar. Right? But what I want to do in this video is to say, okay, we have now taken a basic look at some of the properties of both groups, just general groups, as well as now these things called homomorphisms, the maps between them. But let's now, in this video, and you could probably tell by the section title, is let's start going over specific examples of groups. And what we're going to really be interested in this video is going to be specific examples of finite groups. We've had examples of infinite groups that we've introduced before, like the integers under addition and stuff like that. But we're going to see that there are going to be certain types of groups that are going to be of interest to us when looking at finite groups. And the general idea is to first introduce what those groups are, and second, to really gain an intuition for what these types of groups are. Because as we're going to see as we go further throughout this video series, we're going to be looking at many different types of groups, but we're going to be saying, well, what is that group really like? Or in other words, what is that group isomorphic to? And we could say, oh, well, that group looks exactly like this type of cyclic group. A bit of foreshadowing. Or this type of dihedral group. And we're going to see that cyclic and dihedral groups are going to be the two classes of groups that we are going to be interested in for this video. Okay. So hopefully that makes sense for what we're going to be interested in. Let's start with the first of those two, which is the notion of a cyclic group. So what I'm going to do is just write out the definition up here, and then we're going to go through that together. All right, so we have our first very mathematical definition here for this thing called the cyclic group. Let's unpack what this definition actually means, right? So it says that a group is considered cyclic if there exists some element A, and what we're going to do is we're going to call A, just to put some terminology out there, we're going to call A the generator of this group. But there's going to exist some A such that all other elements of the group, which we're going to denote as B, can be written as B is as some power of A raised to some power. Okay? So how can we understand this thing called a cyclic group? Well, another way of writing a cyclic group is to say that it is a group that can be generated by a single element. So maybe let's just write this, that for part of the intuition, a cyclic group is a group generated by a single element, which I'm going to call A. And it's going to be generated by the generator, which is hence the terminology, right? So we might say, okay, it's this group generated by a single element. What does that mean? Right. So let's start writing some stuff out right here. A notation that we can use to denote a cyclic group is this notation, where we have the generator of the group enclosed by a set of brackets, and this would read as the group generated by the singular element A. Now, if we were to write out the actual elements of what this group would be, let's do that right now. We know that every group needs to contain the identity element. So we're going to have the identity element E, whatever that looks like, in there. Then, if the cyclic group is generated by A, it should probably contain A in it, right? So we have E, we also have the generator itself, A. But then what comes after that? And that's when we can really use this property, or the definition, I should say, right here. This is telling us that all elements of the group B are going to be A raised to some power. So whatever else I write within my set brackets right here, or set braces, need to be A to some power. So we're going to have E, we're going to have A. We can also have another power of A, like A squared. We have A cubed, A to the fourth. And this is just going to keep on going. Every element is going to be some power of A. And eventually we're going to get to A to the n minus 1 in the finite case. And then we're going to stop right here. Now we might say, why are we not continuing? Why are we not writing A to the n as well? And this is where the notion of being a cyclic group, or where the phrase becomes useful. And the idea is that once we get to A to the n, we would say, okay, that is like just looping back around to the beginning of the first element that we've written here on the board. So cyclic groups are going to have the property that, or a cyclic group with n elements, I should say, for finite cyclic groups. They're going to have the property that A to the n loops us or cycles back around to the identity element. Okay, and hence the phrase cyclic, right? So this is how we can denote a cyclic group. And if this has n elements in this group, what we can do is we can denote this as, through another notation, as C sub n, where this is just a group that has n elements in it. Okay. So hopefully this idea makes sense, that a cyclic group, it's a group generated by one element. This is what it's going to look like in the general case where it has n elements. But let's go through some specific examples down here to gain some further intuition for what these cyclic groups are. Cyclic groups can be both finite and infinite, but we're going to be looking in the case primarily where the group is finite. So let's start with that. Hopefully we remember that group elements can be denoted as symmetries. So we're going to go back to one of those examples as I think, even if it is not the most mathematical right away, that it is the best for our intuition. We can visualize groups of symmetries by looking at symmetries of polygons, at least early on. So let's take a look at this object right here, the equilateral triangle. And this triangle, I could denote its vertices as 1, 2, and 3. Okay. And let's say that, for example, what I want to do is I don't maybe want to look at all symmetries of the triangle, but I want to only look at the symmetries that are constructed by rotating the triangle. So only if we were to take this triangle and rotate it here on the board, but maybe we're not going to look at reflections, where we're kind of like flipping it about a certain axis. So if this is the object that we have in question, then we could say, all right, what would each of these elements in the group be denoted as physically with the triangle? And we could start with this identity element. That is essentially the do nothing element. So if we were to take this triangle, rotate it by 0 degrees, so literally do nothing to it, that leaves this thing unchanged. So the act of rotating it by 0 would be the identity element. Next, we would have the generator of the group. And now let's maybe think about what we would need to rotate this by in order to have this structure right here. And I think really too, just to even have a symmetry in the first place, we need to rotate it by some amount so that it looks like an upright triangle after the rotation. And hopefully it would make sense that if we were to rotate this by 120 degrees in either direction, clockwise or counterclockwise, that we would have that property be satisfied. So let's say we rotate this by 120 degrees counterclockwise. So 120 degrees counterclockwise. What that would do is that would produce this picture right here, but then 3 gets rotated up to 1. 1 gets rotated down to where 2 was, and then 2 gets rotated over here. So even though upright it looks the same, you can see that the positions of the vertices look different. And what maybe I'll do is, rather than calling this rotation by 120 degrees, rather than calling it A, maybe I'll call it R for rotation. So going from here to here produces a rotation by 120 degrees R. But of course, now with what it means to have a cyclic group being generated by just one element, all of these further elements right here are just going to be powers of the generator. The power of, in this case, is this rotation by 120 degrees. What I'm saying is that we would get another symmetry, we would get yet another triangle if we were to just apply this same rotation again, if we were to apply R 2 different times. So what that would mean is we apply the 120 degree rotation to this thing twice, or the 120 degree rotation to this thing once, because this already has one rotation applied to it. So if we were to apply yet another rotation of 120 degrees counterclockwise, 2 would go up to here, 3 would rotate down to where 1 is, and then 1 would rotate to where 2 was, like this. So we see that we still have this upright triangle, but now again the vertices are in different places. Hopefully this is making sense, how we can visualize what each of these elements could be represented by. All right. Now let's just try to keep going though. Let's imagine that we were to raise these to higher powers, because we could have higher powers in theory with the notation that we have to describe the cyclic group. And you can imagine if we were to rotate this 120 degrees one more time, or in other words, we were to apply 3 rotations of 120 degrees. Well, 3 times 120 is just 360, right? that is like rotating something by a full circle. So imagine taking this triangle, rotating it by a full circle, and if we were to do that, 1 goes back to 1, 2 goes back to 2, and 3 goes back to 3. Rotating it 3 different times by 120 degrees gets us back to this starting point. It cycles back to the original orientation of the triangle. So another way of describing this is that the identity element is equivalent to rotating this 3 different times. And that right there immediately tells us that if we were to apply the rotation 3 times and get back to the identity, that tells us that we are working not with the general group C sub n, but the specific cyclic group C sub 3. So we could write this out as a group, denoting it as C sub 3, to be the do nothing element, a singular rotation, or applying rotation 2 different times. Okay. Hopefully this makes sense, and why we can think of this as a cyclic group. Now, obviously, triangles are not the only polynomial that exists out there, and you can imagine that we could have a different polygon. Did I say polynomial or polygon? I meant to say that triangles are not the only polygon out there. I hope that's what I said. You can imagine if we had a pentagon that we were interested in, a 5-sided polygon. And if we were to only look at the rotations that leave the 5-sided polygon invariant, to look at the symmetries of the pentagon's rotations, that would produce the group C5. And that would be E, R squared, R cubed, R to the 4th, like this. Right. What I want to make very clear, though, is that, well, first, in general, we can imagine C sub n as just the rotations of an n-sided polygon, or the rotational symmetries of an n-gon. But also, if we were to denote C3 like this, and to denote C5 like this, that would be perfectly acceptable to do. But I want to make sure that we understand notationally that even if we were to write C3 like this, as having R and R squared, and then we were to write C5 containing also R and R squared, R cubed, and R to the 4th, but containing the same letter R, that this R right here is not the same as this R right here. This R, for the rotational symmetries of a 3-sided polygon or a triangle, that would be a rotation by 120 degrees, like what we saw right here. But we could not rotate a pentagon 120 degrees and still leave it looking symmetric, as if we never rotated it. So a rotation in C5 would physically correspond to a rotation of 360 divided by 5, or 72 degrees. So even though we are writing elements of the cyclic group with the letter R, or we often do that, that does not mean that this R is the same thing as this R. These are just, I guess, ways of describing various elements. But R could take whatever form it wants to. In other words, just because this is a rotation by some amount, that does not mean that it needs to be a rotation, the same rotation that is in a different cyclic group. Instead, what we should be thinking about is how are these elements defined within the group. With here, this top example, C3, this R has the property that when we raise it to the 3rd power, we get the identity element. But R down here in the group C5 has the property that if we take R 3 times, we just get back to R cubed, which gives us the trivial statement R cubed equals R cubed. But instead, this element R has a different property. It has the property that if we apply it 5 times, then we get back to the identity. So even though we have the same notation, or we will often use the same notation, just know that these are just ways of denoting general elements, and that they don't necessarily need to correspond to the same physical thing. Okay. Hopefully that distinction makes sense. Now, we are seeing that with the cyclic group that there are these properties that after you raise an element to a certain number, you get back to the identity. Turns out that there is a general term to describe what that is. It's called the order of an element. Let me first erase the board, but then let me write out the definition for what that means, because we're going to be talking about orders of elements a lot. We want to make sure that we distinguish the order of an element from the order of a group, because those are different things. Okay, so we have the order of an element right here, which is different from the order of a group. So let's go through that. So it says that the order of an element A of G is the smallest integer n, such that if we take this element A, raise it to the nth power, it's going to be the smallest power such that we get back to the identity element. Now, if n does not exist, we would say that A has an infinite order. And the way that we can denote the order of an element is to just write the order, or the letters ORD, and then parentheses the element, the order of the element A. And if A to the n is the identity, then the order of A is equal to n. Okay. So this is very different than the order of a group, which is simply how many elements are contained within the group. Let's go through just a specific example involving the cyclic group, or an instance of the cyclic group to help us understand this. So we could have any sort of cyclic group, of course, or C sub n, but if we were to look at C sub 4, that would be the group E, comma, R squared, comma, R cubed. We can imagine these would be like the rotations of a square. We're to rotate a square by various factors of 90 degrees. And C4 would have the property that if we took this element R and applied it 4 times, we would get back to the identity. Okay. This is kind of what we had like in the previous board. But let's now just expand upon what this would mean. We'd say, let's maybe try to look at the orders of each of the elements here in C4. So first, I guess, element that we're going to look at is E, and let's say, what is the order of the identity element? And maybe take some time. I'm going to go through the order of each of these. Let me actually just write these out real quick. So we're going to have the order of E, the order of R, the order of R squared, and the order of R cubed. So maybe what you could do, take a minute to pause the video and try to see if you could obtain what the order is for each of these elements. Assuming we've paused the video. Now, going with the identity element first, we would say, what is the smallest integer that when we raise E to some power, we're going to get the identity back? And we don't need to apply, we don't really need to raise this to any power. We could just say that E to the 1 is just equal to E. I shouldn't even say this is equal, but let me do this. We know that E to the 1 is just E. It's trivially true, right? So the order of the identity element, and this is going to be true for regardless of what group we're working with, but the order of the identity element is just going to be the number 1. Okay. So it is the smallest value that we could get back to the identity. And what people might be thinking here, and something that I initially thought when I was first learning about this stuff, is how come we can't just say E to the 0th power, the identity to the 0th? Because isn't anything to the 0th power equal to the number 1? And isn't 1 the identity? And the answer to that is, well, we want to make sure that we are not thinking of a specific example of a group when we're talking. When I'm saying that the order of the identity is going to be 1, I am not thinking of the specific example where the identity happens to be the number 1. We don't even need to be working with groups of numbers necessarily at all. kind of like what we were just looking at with the symmetry, the rotational symmetries of a triangle. So even though if the identity element is the number 1, and it so happens that we raise something to the 0th power to produce the number 1, this will not, just taking something to the 0th power is not as well defined if we're just working with arbitrary elements that are not necessarily numbers. And because of that, that's why we want to say that the identity just raised to 1 time is guaranteed to equal itself no matter what E is, whether it looks like a number or anything else. Okay, so I wanted to just quickly mention that in case that was slightly confusing. Now let's keep going though. On to the order of R. What is the smallest power we could raise R to so that we get back to the identity? And hopefully this one isn't too difficult in the sense that we kind of have the answer right here. If we take R to the 4th power, we're going to get back to the identity. That's kind of how it's defined. And if we were to raise R to any power less than 4, maybe the 1, the 2, or the 3, that gets us to these elements right here, but it does not get us back to the identity. Okay, so the order of R is going to be 4. Now let's look at the order of R squared. What is the smallest power that gets it back to the identity? And what you might be thinking is, well, couldn't we also just do the same thing, this same property right here, where rather than R, we have R squared. If we raise that to the 4th, that gives us R to the 8th. That's like rotating something, that's like imagining us rotating a square 2 full revolutions by 720 degrees. Doesn't that get us back to the identity? The answer is, well, yeah, it does. But that is not how the order of an element is defined. We would not say the order of R squared is equal to 4, because there is a smaller integer than 4 that loops us back to the identity. And hopefully we can see that there is a smaller value than 4, which is 2. If we took this element R squared, raise it to the 2nd power, that gives us R to the 4th, which also brings us back to the identity. So because we have found a smaller integer, that when we raise R squared to that, we get the identity, we would say that its order is that smaller number. We would say the order of R squared in this case is the number 2. Okay. Hopefully we're seeing how this is working. Now let's go on to this final example, order of R cubed. And maybe you can imagine that if this starts getting more complicated, and we have larger cyclic groups or just larger groups in general, because the order of an element is a general concept that can be applied to any group. We're just looking at it in the context of cyclic groups because we just introduced those. But let's start taking various powers of R cubed and seeing how many times we need to multiply this by itself in order to get back to the identity. So R cubed raised to the 1 is just R cubed, right? So that gets us to its element, but that is different than this identity right here. If we were to then if we were to then take R cubed and square it, that would get us to R to the 6th. And we say, okay, if this is R to the 6th right here, we could rewrite R to the 6th as R to the 4th times R squared. R to the 4th, we said was the identity. That's a property of the cyclic group C sub 4. So this is just E times R squared, or gets us back to R squared. So what I'm trying to say is that if we took this element and applied the binary operation R cubed times R cubed, that would actually get us back to this element, R squared, which is not the identity. So the order of R cubed can't be 2. Let's just keep on going, and hopefully you can see the pattern. If this were to become a 3, then we get R to the 9. Let me just write this out. R cubed cubed, that's R to the 9, which can be decomposed as R to the 8th times R, which is E times R, which is just R. So if we were to take this element, R cubed, apply the binary operation to it 3 different times, so we get R cubed times R cubed times R cubed, that would bring us back to this element, R. So the order can't be 3. If we were to apply it a 4th time though, we would get R to the 12th, which eventually would get back to the identity. So the order of R cubed, just like the order of R in this case, would be 4. But more importantly, though, hopefully we see how we can obtain the order of a given element. And we just so happen to do that in the context of a cyclic group right here. All right? So hopefully this makes sense. Now, admittedly, when we talk about the order of an element, it is very easy to get that mixed up with the order of a group. And it seems like there should be some sort of connection between the order of an element and the order of a group. Otherwise, like, why would we call those the order of anything in the first place, right? And what we're going to see, I'm going to write out a claim real quick that's going to show that, well, it turns out there is a connection between the order of an element and the order of a group. So let's go through that next. Okay, so we have this interesting claim right here. Let's go through it and then understand what it means. So it says for an element of the group, of any group, so some A and G, there are a couple things that we can say about this element based off of what we've been talking about so far. The first is kind of the left-hand side of this equation, which is to say that we can take the order, or we can look at the order of this element. In other words, what's the smallest integer, that when we raise a to that power, we get back to the identity. Another thing that we can do, and we haven't talked about this as much, even though we could probably infer it, is that regardless of what element we have, for any general group, we can construct a corresponding cyclic group. We can look at the cyclic group, the thing, if we ignore the vertical lines for now, we can take a cyclic group generated by this element, whatever that element happens to be. We are allowed to do that. And in some cases, the cyclic group, brackets with A inside it, that might be the entire group itself, or it could also be a subgroup of G. Just to really quickly go through an example of what that would look like. C4 is a group E, R, R squared, R cubed, with the property that R to the fourth equals the identity. The cyclic group generated, another way of writing this is the cyclic group generated by R. But if we were to look at the cyclic group R squared, that would be various powers of R squared. And we would have R squared. You can imagine if we raised R squared to the second power, though, we'd get the identity. And then if we raised it to a third power, we'd get R to the sixth, which is the same thing as R squared. So we can look at an element of C4. R squared is in C4, and the cyclic group generated by it is a subgroup of the original group that we were looking at, C4. So we can take the cyclic group of any element. We can also take the cyclic group of R cubed, and that would bring us back to just the original group, C4, like this. Okay. Point is, hopefully we get it. The point is that we can take the cyclic group of any element of the cyclic group generated by any element of the group. And it turns out that if we take the size, that's what the vertical brackets mean, if we take the size of this cyclic group, that is going to be equal to the order of the element. Or potentially more confusingly, the order of an element of a group is equal to the order of the group, order of the cyclic group generated by that element. You see how we're going to be using the word order a lot here. But let's go through this to make sure that this actually makes sense. Now, we could do this for both the finite or the infinite case. And what I mean is that in the case where the equation is finite or infinite, this should still apply. Let's start actually with the infinite case. I think it's probably a bit shorter to see. And let's suppose the left-hand side is infinite, so that the order of this element is infinity. What this tells us then necessarily is that if we were to take A, raise it to some power, we are guaranteed, well, let's say, for example, I take A, I raise it to the nth power, and now let me also suppose that I take A, raise it to the mth power. And maybe in general, we'll just we'll assume that m is larger than n, doesn't matter. But I were to raise a, which has infinite order, to two different powers, it is guaranteed that these elements are not going to be equal to each other. A to the n is not equal to a to the m. And here's why. Let's suppose the opposite is true, that a to the n is equal to a to the m for some values of m and n. Then what we could do is we could say that a to the m inverse is just, or let me do this, a to the n inverse, it really doesn't matter, but a to the n inverse is a to the minus n, like this. And it's going to have the property that a to the minus n times a to the n gives us the identity, right? But if we were to suppose that a to the n is equal to a to the m, they are equal for some value, then I could replace a to the n here with a to the m here. Or in other words, I would get that this quantity is just a to the m minus n gives us the identity. Now what does all this mean? What this is saying is that if the left-hand side is infinite, that should tell us the right-hand side should be infinite. Or in other words, the order of the cyclic group generated by this element must also be infinite. Let's write out what that means for the order of this group to be infinite. We said here that a cyclic group is just going to be e times a squared. Or actually, let me do this. It's going to be e times a, or a squared, and so on. And then we could also have negative powers too if we're looking at its inverses. So a to the minus 1, a to the minus 2, and so on. Let's do this. A little cramped here. There we go. So again, the cyclic group is just the group generated or by all powers of this element A. If this group is infinite, which is what we're saying the first case is, where the left-hand side is infinite, then that means there should be infinitely many different elements in here. And if there are infinitely many different elements in here, that means that regardless of what powers we choose within this group, regardless of what m and n we decide to pick, that it's guaranteed that they need to be different. Because if they were, right? I hope I'm not over-explaining this. Because if they were the same, if we were to find some instance of some power of a in here and some other power of a in here, where a to the n all of a sudden equaled a to the m, then that would lead to this equation where a to the m minus n equals e. We might be saying, well, why is that a problem? Well, this equation right here would tell us that the order of a is equal to m minus n, or some smaller value of it, some smaller multiple of it. So basically, if a to the n equals a to the m for some values of m and n, then we're going to get some finite order. So which is a contradiction. So because the order is infinite, that means all the elements of this group need to be different, and hence the order of this group must be infinite. I hope that makes sense and that's not too confusing. But yeah, so that's going to be the infinite case. The finite case too is very similar logistically here in terms of the proof. If this is going to be finite, then let's now say that the left-hand side is some finite value. So we're going to say that the order of this element is equal to k. Another way of saying this is that k is going to be the smallest power that we could raise a to and get back to the identity. Right? And what we would like to then show is that the right-hand side must also be k. So we'd like to show that the cyclic group generated by a, its order is equal to k. Okay. So hopefully the finite case scenario at least starts to make sense, what we're trying to prove. First thing is that we know that the cyclic group, the order of the cyclic group cannot be smaller than k, because k was the smallest value that we could raise this element to and get back to the identity. It was defined that way in the order of an element. This had to be the smallest number. So in other words, if we took a squared, a cubed, all the way through a to the k minus 1, none of these elements right here can be the identity element. And because if any of these were the identity element, then the order would be just whatever one of these exponents was. It would be either 2 or 3 or 4 all the way up to k minus 1. But because we said the order was k, that means that none of these can ever equal the identity. So the cyclic group generated by A, it's going to contain all powers of A, right? All unique powers of A. So it's going to contain these k minus 1 elements in it. So we know that the cyclic group must have at least k minus 1 different elements. We have 1, 2, 3, 4, all the way up through k minus 1. And then we say, okay, well, what would the kth element be? And that was established by this condition. We said that if the order of A was equal to k, then a to the k needed to give us e, like this. Now, so this, up until this point, tells us that the order of this cyclic group would have to be at least k different elements, but could it be larger? Obviously, we're trying to show that it's not, but could it be the case where this cyclic group has some larger power? And the answer is simply no. Let's, for example, just say that we were to look at a to the k minus 1, a to the k plus 1. This is larger than a to the k. And maybe we want to say, well, what if the order of this cyclic group generated by A what if this right-hand side is equal to k plus 1? And we'd have to say, well, that can't be the case because a to the k plus 1 is just equal to a to the k times a. And because the order of A is k, then this is equal to e times a, which is just a. And that element, a, is contained right in here. So what we've just shown, and let me summarize this. What we've just shown is that there needs to be this many distinct powers just from the left-hand condition alone. The identity element gets introduced as the kth element, which also gets imposed by this condition right here. And then we can't have any higher powers because of this condition, a to the k being e. We're going to see that an example of a higher power is just going to loop back to one of these other elements in the group. Therefore, if the order of A is some finite value k, then the size of its cyclic group generated by A must also be that same size. A lot of stuff going on, but hopefully this makes sense. And I would recommend taking some time to pause and think about this if it doesn't. But yeah, let's keep going. We've talked a bit about cyclic groups now at this point. I will also want to introduce the other sort of specific group type that you'll have seen in the title of this video called dihedral groups. So I'm going to erase the board and then we'll go through that next. All right, so now moving on to these things called dihedral groups. Let's read what the definition of these things are. So dihedral groups, which are in general denoted as d sub 2n, that is not a typo, d sub 2n, are going to be the symmetries of a regular n-gon, or in other words, an n-sided polygon. So they contain n different rotations and n different reflections for a total of 2n elements, hence the subscript 2n in it. Okay. So I think it's probably best to understand what these types of groups are by just going through a simple example, probably using the same triangle, but again, the regular triangle. But of course, this is can be applied to any regular n-sided polygon. So if we are working with the triangle, the regular triangle, that would be a regular 3-dimensional polygon. So we would be looking in the case where n is equal to 3. And if we're looking in the case where n is equal to 3, the corresponding dihedral group is going to be d sub 2 times 3 or d sub 6. So we're going to be interested in this group D sub 6 right here. Okay. Now, what I would like to do is just to see, okay, how does this framework operate? So it's going to contain n rotations, and if n equals 3, it's going to contain 3 rotations of this triangle. So if I were to draw this triangle out, I ultimately draw it out 6 times, but you can imagine that this is partially why I want to have a relatively small example, because if we have larger examples, the size of this is going to get large, right? But it's going to say that it's going to contain n, or 3 rotations, and then also 3 reflections. So let's see what that would look like. If we were to have just starting vertices 1, 2, and 3, like this, we know that there is always going to be a do nothing transformation, and that acts as the identity element. So if we were to take our triangle, kind of look at it and be like, all right, we transformed it by doing nothing to it, that would be the identity element, E. So D6 contains E. Then we could say, all right, let's look at another way of saying E2 is a rotation by 360 degrees, one full revolution. So that's another way of saying the do nothing transformation. And because of that, that would be considered one of the n, or one of the 3 different rotations of this group. If we were to then now consider rotating it by 120 degrees, then 1 goes here, 2 goes here, and 3 goes here. So this is going to give us 1, 2, 3, like this. That would be a rotation that leaves the triangle looking upright, and we can denote that with the letter R. This is nothing new so far from the cyclic group that we've been looking at. We could apply the same thing again, and like what we've done, where 3 goes down to here, 1 comes over here, and 2 goes up to here, and we're going to get 3, 1, 2. That would be the act of applying that 120 degree rotation, counterclockwise rotation, 2 different times. That would be R squared. But now, how are we going to denote these elements down here? It's also going to contain 3 different it's going to contain 3 different reflections. So what does that mean? Well, what we could do is you could imagine if this was our starting triangle, the top left one, we could draw out 3 different axes that I'm going to draw with these dotted lines right here. And you can imagine reflecting the triangle across one of those 3 different axes. By doing that, you are still going to be left with an upright triangle regardless of how you reflect it across each of these 3 axes. But that will, so because of that, it's going to lead to a different symmetry. So let's see what that produces. If we were to reflect it across this vertical axis right here, you can imagine taking the triangle, and this would be like, I don't have a triangle on me, unfortunately, but you can imagine taking a book. If we were to reflect it about this vertical axis, that would be rotating it by 180 degrees about that vertical line right there. So by doing that, this top vertex 1 would be left unchanged during that reflection. So this would be 1. But then 2 and 3 would swap places. So now 2 would go here and 3 would go here. So we have 1 right here, we would have 3 right here, and then we'd have 2 right here. Let's imagine a different axis now. Let's imagine maybe this one going from the bottom left to the upper right. If we were to reflect the triangle about this axis, that would be like fixing 2 in its original spot, so keeping 2 right here. But then taking the triangle and sort of rotating it by 180 degrees, so now 3 is in the 1 spot and 1 is in the 3 spot. Hopefully we can imagine that visual rotation, even though I don't have a triangle on me. So this is then going to be 3, this is 2, this is 3, and this is going to be 1. And then for the final one is just the last one. It's like fixing 3 down here, and then that's going to swap places with 1 and 2. So these are a couple different, or 3 of the reflections, But notice that I started to write out this group D sub 6 here as E, R, R squared, and so on. But so I would like to have notation to describe these, what's it called? These three reflections right here. And I don't want to be putting like R1 for reflection 1, R2 for reflection 3. That can get quickly confusing. So typically the notation that we use is we'll use the letter S. And this is just a convention. There's no rule on this, but this is what we typically see. Is that R will denote a rotation, in this case by 120 degrees. And S will denote a reflection, typically by one of the three different axes. Now you might be saying, well, there are three different axes, right? Well, we're just going to pick an axis and see how the rest of the elements can get generated from just one of those axes. Here's what I mean. Let's just pick the axis to be the vertical one, because I think that's probably the easiest to see. So we'll erase these other two dashed lines like this. So this is going to be our vertical axis. And reflecting the triangle about that vertical axis is going to be the active performing S. So going from this triangle down to swapping 2 and 3, this is going to correspond to the element S. Okay? So hopefully that makes sense. Now let's say that we want to give elements names for both this guy and this guy. This was E, this is R, R squared, S. But what are these going to be named? And what we can do is we can actually name these elements in terms of the elements that we already have. So let's see how to do that. I want to start with this one over here, because I think it'll be easier to see. And let's say that we start with this triangle, so 1, 2, 3, perform some manipulation to it that gets us down to this triangle, 2, 1, 3. That's where the vertices are. How could we denote this element? And we can say, well, what we can do is we can first take this triangle and we can first reflect it across that vertical axis. We could go from here down to here, which would give us 1, 3, 2. So that would correspond to first applying the reflection about the vertical axis. Then once we are in that position, then we can perform a rotation by 120 degrees. So let me actually, just to make sure this is very clear, let's say R corresponds to a, not 110, 120. R corresponds to 120 degrees counterclockwise rotation, and then S corresponds to reflection about vertical axis. Okay, and so what we've done so far is we've taken S by reflecting across the vertical axis. Then after that, we apply R to it. We apply a rotation of 120 degrees counterclockwise. And you can imagine if we're at this point, we now rotate the triangle by 120. 2 goes up to here, 1 goes down to here, 3 goes over to here. That's exactly what we have right here. So if we first apply S and then we apply R after that, we get the element RS. And hopefully you can see a pattern here, right? So if this is RS. If we have E, R, R squared, S, RS, you can imagine what the last one is going to be. It's going to be R squared S. Let's make that curly a little better. All right. And I would encourage you to try to work through this yourself if it's unclear, to see that this picture needs to correspond to first applying a reflection across the z-axis, the vertical axis, and then applying 2 different rotations once we get down to this point right here of 120 degrees. Okay. So hopefully this makes sense. And in the general case, this is for D6, right? But in the general case, D sub 2n, what we're going to have is we're going to have a group that's going to be E, R, R squared, all the way up through R sub n minus 1. These first n elements are going to be the n rotations. And then we're going to have S, rs, r squared s, all the way through r to the n minus 1s. And the general dihedral group d sub 2n is going to look like this. And hopefully this makes sense why it's 2 sub n, right? Because this subscript denotes the number of elements in our group, or the order of our group. Like D6, there are 6 elements in the set right here. Okay? So hopefully this makes sense. What I think I want to do now is, now that we've introduced both cyclic groups and dihedral groups, I want to just briefly, I'll keep even the definition up here, but I just want to maybe erase the bottom half of the board to quickly go through just some notation that we're going to see to compactly describe both cyclic and dihedral groups, and then we're going to call it for this video. Okay, so we've written out some notation right here, and I just wanted to go through this. Let me maybe put a bar, I guess it doesn't really matter, but I wanted to go through this just so we're familiar with this going forwards, because these are, we could write something as C sub n or D sub 2n, but really what does that mean? Like, what are the algebraic properties of these groups? And let's start with C sub n. So C sub n is going to be a set of brackets, and the set of brackets is going to denote that it's a group. And this is kind of like the set notation, where we would say that, like, if we had a set S, it's going to be the set of some elements such that X blah, 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 satisfies some condition. It's the same thing right here, except now we're using brackets to denote that we're working with a group rather than just an arbitrary set. So C sub n is going to be the set of elements A, such that if we raise A to the nth power, we're guaranteed to get back to the identity element. And any cyclic group is going to have this property right here, that if you have C sub n, regardless of what element it is, and I recommend you trying this out for some small values of n, so maybe C sub 2, C sub 3, C sub 4, if you take any of those elements and raise them to that nth power, you are going to get back, and you're going to loop back to the identity. So this is how the cyclic group is really defined structurally, that all of its elements, when raised to the nth power, produces the identity element. Okay. Now for the dihedral group, it's slightly more complicated, but I think it should hopefully still make sense. If these are the symmetries of a regular n-dimensional polygon, it's going to be elements composed of both rotations R and reflections S, such that if we rotate an n-sided polygon n different times, so like if we rotated a triangle 3 different times by 120, or rotated a square 4 different times by 90 degrees, we're going to get back to the identity. But also, so that's the r to the n equals e condition, similar to what we have with here with the cyclic group. But there's this additional thing as well. There's this s squared equals e. So let's describe what that is real quickly. And hopefully this makes sense too. But like, you can imagine if we had our triangle right here, this was 1, this was 2, and this was 3. If we applied a reflection about this axis one time, or we took s, that would cause us to sort of rotate this by 180 degrees in the plane, and that would bring us to this triangle right here, where we have 1, now 3 is on the left and 2 is on the right. This would be s. But then imagine we apply s one more time once we're already here, about the same axis. That rotates it, or reflects it again across this axis, so now 2 goes back to here and 3 goes back to here. That is the same thing as if we had done nothing. So what I'm trying to say is that dihedral groups are defined as some elements, no matter what they look like. We're going to generally call them R and S, where n rotations brings us back to the identity, and also any 2 reflections also brings us back to the identity. So this is the first condition right here. It turns out there is another condition, and what I would recommend doing, because to me this is probably the most intuitive way of understanding this last condition, is to just work through the small example of the triangle yourself. And maybe what I'll do is I'll hold off on doing that for now, But if there's enough feedback for people that would like to see why this condition is true, I'd be happy to do that. But what we're essentially saying is that this second condition right here must also be true. This is an inherent property of dihedral groups. And we'll see that when we work with dihedral groups, we'll be able to make use of this equation. What this equation says is that if R is a rotation by some number of degrees, R inverse is going to be just that same rotation in the opposite direction, because if that essentially undoes the original rotation R. But another way of denoting a rotation in the opposite direction is to first apply an inverse reflection, which is kind of just a reflection itself, then apply the standard rotation R, and then apply reflection again. So this product of three different transformations is equivalent to just applying the inverse rotation. And if you have a set of elements where both of these conditions are satisfied, then you're going to have the dihedral group. Okay. So again, hopefully this makes sense. And more importantly too, if parts of this do not make sense, and especially this part, because I want to keep the video somewhat compact, please, I would strongly recommend trying it yourself. I'm happy to show why this would be the case in the instance of a triangle, but hopefully we can work through, you're able to work through that. Okay. But yeah, that is going to be this, that's going to be it, I should say, for this video. Just introducing these things called cyclic groups and dihedral groups. In the next video, we're going to start to talk about these things called direct products of groups. And once we have that, we're going to have all the tools that we need to say that whatever small finite group we're looking at, that it's really going to, at the base level, is going to be isomorphic or have the same structure as either some cyclic group, some dihedral group, some other fundamental finite group, or a direct product of those groups. So thanks so much for watching, and I will see you in the next one.